Welcome to a video on filter approximations. So in this video we will look at some of the terminology that we will be using. Then we will look at some filter approximations and compare them. So we will be looking at the Butterworth, the Bessel and the Chebyshev approximation. And then how do we design filters from using tables. Okay, so we are doing this before we go to the low pass and high pass KRC filters so that we can design proper filters. So a table has normalized values in it, so all the complicated math has been done for you, so you didn't have to go through all that rigmarole again. Everybody has done it millions of times. So I feel if you just want to design a filter, just use a table. It's as simple as that. So let's jump into the terminology and then the different approximations. Okay, so passband, stopband, and ripple. The passband is the part of a frequency that will be let through of a filter, and the stopband is where we should have little or no signal left, and this area in between is the cutoff region. So this is all based off a brick wall kind of filter. So the perfect filter would be perfect passband and then just stop. Right. As you can see, there is a ripple defined in the passband and in the stopband. Some filters do have this ripple effect in the stop band, and a filter like the Chebyshev has unevenness in the passband right here. So that is called a ripple. So during the passband, the gain in the filter will not be equal everywhere. Okay, that is done to get a sharper kind of cut off. Okay, so passband ripple and roll off. So the Chebyshev, we have these ripples, and then it can cut off much sharper in the cutoff region before we get to the stop band. And we will have more ripples the higher the order of the filter. Right. The pass band for the other filters, you will see if the order goes higher and we increase the Q factor, we can maximize the pass band. And you will see that they all cross in the same point here at the minus 3 decibel point, or 0.707 volts per volts. Okay, and as we increase the order of a filter, the closer this starts to become to that brick wall approximation that we actually want. Okay, so this is also the roll off or the sharpness of a filter right here. This how quick it starts to cut off, and the roll off is how long does it take to before it cuts off. Okay, now in some of these approximations, every approximation has a advantage and disadvantage. Okay, so we will look at those for each filter in a moment, comparing them all against one another. But the Chebyshev filter has this very strange phase plot right here, right? And the Bessel has a very smooth phase. Now, this very sharp kind of phase difference for frequencies causes a bit of a time delay in your response and causes ringing in the time domain. Now, ringing is when you have a bit of oscillation or instability in your filter. So the Bessel is a very stable filter, and the Chebyshev is a bit of an unstable filter. And we can see that in the passband, the fact that we have these ripples, and that right there is considered to be a very high Q value, and that will cause oscillations, right? So the Chebyshev is a bit of an unstable filter, and the Bessel is a very stable filter, and this comes from our phase response. So around the cutoff frequency, our Chebyshev has a very quick change in phase, where the Bessel has it gradually. Okay, so the difference between the Chebyshev and the Bessel is when we insert the step response, the Chebyshev you can see has a very smooth transition, and the Bessel, and the Chebyshev has this really unstable response to a step. Another thing that you can see is the Bessel has a very short time delay, and the Chebyshev has a very long time delay passing through the filter. Right. So let's look at the three filters separately. The Butterworth has a constant or flat passband, no ripples at all. It has a 20 decibel per decade cutoff rate, and for each order, this will increase. So for second order, 40, for the third order, 60, and so on and so forth. We will be looking at a seventh order for each one of the filters in comparison later on in this video. Right. The the Butterworth has an average signal delay passing through. It is kind of between the Chebyshev and the Bessel approximation. The distortions is average. There is minimal ringing when we have a pulse response, and we can minimize the cost using equivalent components with the Butterworth approximation. Basically, almost all the components except for the Q factor in the KRC filter will be the same components. Okay, so if the amount of if the components has the same value, that reduces the cost quite significantly in a production run. Okay, the Butterworth is a very typical filter choice because it is right between the Bessel and the Chebyshev. It is the best of both worlds approach. Right, the Chebyshev approximation. It has passband ripple, so not everywhere across the passband you will have the same gain, but it has a very sharp initial cutoff rate. So when we reach the cutoff frequency, the cutoff rate will be very, very rapid. Okay, so this maximizes the passband reach. So if your passband is 1 kilohertz, you will almost have a cutoff immediately at 1 kilohertz. There is no slow decay towards that point, it will just cut. Okay, same cutoff rate, 20 decibels per decade, but we have a very long signal delay around our cutoff frequency, which will cause some distortions if any frequency entered which is close to your cutoff. Okay, so if you're not bothered about the ripples or that, and you just want the frequency band to immediately stop, the Chebyshev is a good filter to use. Okay, so but we will have ringing and large distortions and delays, and the Chebyshev is extremely sensitive to component choices. Each and every component will be different in a Chebyshev. Okay, also the Bessel, but the Bessel is not as sensitive for a couple of ohms difference in it for a choice. Okay, so Bessel has a constant passband with no ripples. It has a very slow cutoff rate. It has short signal delay. There's no ringing when there's a pulse response, and there is absolutely no distortions. So if you need to, let's say, sample music or something, the Bessel approximation would be the best, since there is no time delays or minimum time delays and no distortions in the output. So this is a very good filter to have right after, right before a ADC of some sort, and you just need a nice cut off with no distortions whatsoever. Then the Bessel approximation would be the best option. Right, so if we look at the three on the same boat plot, the Bessel is the red, the Butterworth is the blue, and the green is the Chebyshev. So you can see the Butterworth is right here in between the two. The Bessel has this long cut off and this very high bandwidth right here, but it starts to cut off really early. The Butterworth, you can see, is right in between the two, even here at the -3 dB point. Right, and it maximizes or tries to maximize the passband. Right, the Chebyshev, you'll see that there is a bit of a up, and then it cuts off really sharp, and then it follows the -140 decibels per decade. This is a 7th order filter, 1 kilohertz design, 35 dB passband gain. Okay, let's zoom in on this part. So this will make things much clearer for the, this is still from 10 hertz to 1 kilohertz. So the Bessel, very long kind of cut off, very slow to cut off towards 1 kilohertz right here. The Butterworth is in the between, and we have the ripples for the Chebyshev, but it immediately crashes at 1 kilohertz like this. Thing to note, if you count the humps, you can tell the order of a Chebyshev filter. So 1, 2, 3, 4, 5, 6, 7. This is a 7th order Chebyshev, and this is a 1 dB ripple, and if you look at the ripple here, it is 1 decibels. Right. Phase response. Chebyshev around the cutoff, this really sharp cutoff. Butterworth, kind of slow, and the Bessel is really slow in the cutoff region right here. So this is what makes the Bessel quite stable. So if we look at the time delays, the Chebyshev has a very long time delay before we get to the cutoff in any case, 1.2 milliseconds. That is quite long. The Butterworth 0.8, the Bessel 0.4 millisecond delay. But if you look at the Bessel, it is very smooth until it goes down to 0 milliseconds. The Butterworth, little bit of a distortion, and then it goes down to 1 milli. But the Chebyshev, there is a huge distortion at the cutoff in terms of time delay. Right. Pulse response. So if we insert a pulse into each one of these filters, we can see the time delay. Bessel having the least, Butterworth in the middle, Chebyshev having the longest. No ripple for the Bessel, minimum ripple for the Butterworth, and large distortions for the Chebyshev. Right. So those are the three main filter approximations, and we can design them from tables. Right, so what's going to happen is, let's take a 7th order filter as an example. All of these were 7th order filters, and this is just a low pass KRC filter. If it's a high pass, then all of these will just be the high pass KRCs. Now each KRC section has a frequency that you can design for and a Q factor like that. And each one has an order of 2. So for a 7th order filter, 2 plus 2 plus 2 plus 1 is 7. So we can cascade these filters one after the other, and we can design them separately. So each one has a frequency and a Q, frequency and a Q, frequency and a Q. And if a filter is an odd number, you need to add a first order filter, and you can do some gain correction if needed. Okay, each one of these stages have a gain of its own. Okay, and the gain is responsible for the Q factor. So gain multiplied by gain multiplied by gain multiplied by another gain would be the final gain of your filter. So it's a multiplication of each, and if you have a final gain that you should reach, you can do that with another non-inverting amplifier. Okay, please do not try and correct the gain using these stages. You will just raise up the Q factor and perhaps cause some oscillations in the process if you push one of these filters into instability. With Chebyshev, you can already see that there is instability due to the positive feedback and the high Q factors. Okay, so you can just cascade these filters. If it's an odd number, you add a first order and you're finished. If it's an even number, you don't need this right here, but you can still do the gain correction with the extra amplifier. Right, so that is why I want to do or look at designing from filters before I get to the low pass and the high pass KRCs. So this is the aim, is that we can build proper filters from our approximations using the KRC in Cascade. Okay, so designing from a table, it is a cascaded design as we saw, and the tables uses normalized values. So everything is based off a 1 Hz filter. So you will either multiply or divide the frequency with the value in the table to find out what frequency you're designing for in your KRC filter. Right. Now, for odd designs, we have second order sections. So for a third order, it would be n plus 2, n plus 1 is a third order filter. Okay, so you can use the first order stage at the end to do your gain correction. For even KRC filter, n is 2, n is 2 is a filter of order 4, and you must add an extra gain correction stage if needed. Right, there is unity gain designs available, but typically for components and whatnot, the even component approach is very typical. But we will get to those in the videos for the low pass and high pass. Right, let's have a look at the tables. There is 4 tables here, so I'm just going to talk on one and show you the others. For a second order filter, there is only 2 values in the table, so this is just one KRC filter. For a third order, there is 3 values in here, so you need to add a additional first order stage using 1 for the frequency value. So this is a 1 Hertz normalized table. Okay, we're gonna denormalize these values when we're designing an actual filter. Okay, 10th order filter. There is 10 values here, 5 frequencies and 5 Q factors. So it's 5 KRC sections like that. Okay, the 7th order that I used in the simulation is that one. So it had 3 KRC sections and 1 first order section. The Butterworth is the easiest to design. As you can see, all the frequencies throughout will be the frequency that you design for. In any case, it's the Q factors that's important. Okay, for Bessel, there will be different frequencies, and you can see that they are kind of spread out across the spectrum to give you that very long cut-off rate in the end. Okay, and it uses very low Q factors mostly. Okay, so that we don't have too much phase response or too many delays or instabilities in our filter. The Chebyshev, you can see that it is quite aggressive on the Q factors for the initial stages, and that is what gives us those ripple values. This is a 0.1 decibel Chebyshev approximation, so the ripple for this one is quite small. And then we have the 1 dB Chebyshev that we had, and look at this aggressive Q factors right here. Okay, that is going to give us that little ripple in the passband. And that is it for filter approximations. See you in the next 2 videos for high pass and low pass filter designs using these tables. Thank you for watching.